Hello everyone and welcome back to Solid State Physics in a Nutshell, brought to you by the Physics Department at the Colorado School of Mines. My name's Eric.
And I'm Nicole.
Our goal today is to introduce how vibrations behave in a one-dimensional crystal. Up to this point, we've considered solids where atoms are stuck in their positions within the lattice. But in reality, we can think of our atoms as simple harmonic oscillators, which have a ground state energy and an associated vibrational mode even at 0 Kelvin.
Really then, we should be thinking of crystals as dynamic structures, and so this rigid, boring picture is actually wrong. In later videos, we'll see how vibrations play a role in crystal properties.
Yeah, vibrations are really an inherent part of crystals, and we should keep that in mind whenever we think about crystal properties. But today, for now, we'll keep things simple and look at how vibrations behave in a one-dimensional crystal. Additionally, we'll treat the bonds between the atoms as springs, and only look at vibrations that propagate longitudinally or along the direction of the crystal. Nicole, why don't you set up the crystal?
Sure. So we'll want to first construct our lattice without vibrations, which I can draw like so, where I'll denote the position of each lattice point with the integer n, n plus 1, n plus 2, etc. Then let's put one atom at each lattice point so that their spacing is given by a.
Now we'll want to define the position of the atoms as they are now with no vibrations as x sub n. And in a second, when we invoke vibrations within the crystal, we'll also define a displacement function u sub n, which describes atom n's displacement from this original configuration.
When you say vibrations, how much are we expecting the atoms to oscillate? Can't we just use Hooke's law to approximate the force from the bonds on the atoms?
Yeah, but we're going to need to be clear on what we're defining as the distance part in Hooke's law. In our case, the force on an atom comes from the difference in u between atom n and its neighbors n plus 1 and n minus 1 times the spring constant. But now we need an actual expression for u.
Seems to me like vibrations can act just like plane waves, so why can't we use that form for our displacement wave u?
Yeah, let's do that, but with some slight differences. Instead of using k for our wave vector, we're going to be using q. Here, we're running contrary to Kittel's notation of a capital K.
Good, not another k variable. And we have x sub n, our original atom position before vibrations, along with a time-dependent portion. Now that we have this expression for u, we can do some plug and chug through Newton's second law and eventually get to this equation.
Notice that we no longer have an explicit time dependence, but that's okay. Really what we want is the dispersion relation, which relates our frequency omega to our wave vector q. And moving things around, we get a dispersion that looks like this.
Eric, so far this looks like a big jumble of math. How does this tell me anything about the displacement of our atoms?
We can dump this dispersion relationship back into our original displacement wave expression, and now we have a relationship between u as a function of omega and time.
Maybe we should see an example to flesh this out.
So for the moment, think of a wave with a really long wavelength compared to the interatomic spacing a. Like say I smack the table really hard.
Okay, so you'd be sending in a sound wave.
And what's the wavelength of a sound wave?
Anywhere from 20 millimeters to 20 meters. Much, much bigger than our interatomic spacing a.
Right. And if we draw our 1D atomic chain, and then draw our displacement wave, each of our atoms are displacing in basically equal amounts at some time t.
As if they're all locally moving in phase. Now let's bring this back to the dispersion.
Remembering that the magnitude of our wave vector is 2 pi over the wavelength, it's safe to say q is pretty small. So small that it's barely shifted off the origin in this graph.
So down near the origin, we're talking about waves that have such long wavelengths that the local displacements are close to equal.
Right, so let's look at a much, much shorter wavelength, say 2a, which puts q here at pi over a, at the local maximum of the sine curve. Then if we draw our lattice and our displacement wave at some point t equals 0, these atoms experience positive displacements, and these atoms experience negative displacement.
Then let's look at it at some time t later, and the peaks and troughs have switched, so the atoms are moving opposite their neighboring atoms, as if completely out of phase, right?
Yeah.
Then, if we took a wave of wavelength 4a and looked at the displacement wave at two different times, we should see partially out of phase movement of our atoms.
And a good way physically to think about the rise in the dispersion relationship is through energy. Higher frequency waves have more energy. Similarly, the more you compress a spring, as we saw in the out-of-phase motion for Q equals pi over A, the more energy you have stored in the spring.
So we've done a fair bit today. It might be a good time to do a recap.
Yeah, so we started with a one-dimensional crystal, where we treated the bonds between atoms as springs. From that, we developed an expression for the force acting on one particular atom at position n.
And then, using a plane wave approximation for the displacement, we were able to develop a relationship between the wave vector and the frequency of the atom oscillations. We also found that the motion of the atoms starts as in-phase movement near the origin and slowly becomes more and more out of phase.
Okay, we've gone through a forest of math today, but it's nice to see there's a physical significance to the dispersion relationship. Next time, we'll talk about allowed values of Q and what the slope of our dispersion can tell us. Thanks for watching today's installment of Solid State Physics in a Nutshell. See you next time.